So why does ice melt when we put salt on it? Hopefully you've already taken a look at this week's little magic trick, and we know that this does happen. We see them putting salt on the roads in the winter. So why does this happen? Well, first we need to understand a little bit about water and some temperatures involved to better understand that. And the temperature scale that we're going to use the most in science is this Celsius temperature scale, the first one that you see. Often you're probably accustomed to using the Fahrenheit scale, which is to the right. But at 0 degrees Celsius, 32 degrees Fahrenheit, that is when water freezes. So that's the first temperature that you're going to need to know, that is when water freezes. And that's the same temperature at 32 degrees Fahrenheit. Water freezes. At 100 degrees Celsius, water boils. That's the same as 212 degrees Fahrenheit that water boils. And so those are the first two things that you're going to need to know. So keep those in mind to better understand why salt is going to affect those temperatures. And it's something that we call colligative properties. So when we have water as our solvent and we add a solute to the water, it's going to change the properties of the water. And this is something known as colligative properties. This is why the salt causes the ice to melt. It's something known as freezing point depression. We also have three others: boiling point elevation, vapor pressure lowering, and osmotic pressure that we're going to take a look at this week. And of course, we've all seen this before. We've all seen the Del Dot trucks on the road melting the ice so that we can drive safely. Now, of course, you might not like this for your car because it might cause some of the metal in your car to rust, but it's safer because it's going to lower the freezing point of the ice. We know that water normally freezes or melts, if it's ice, at 0 degrees Celsius, 32 degrees Fahrenheit. So instead of the water freezing at 0 and 32, it's going to freeze at about -7 degrees Celsius and about 24, 25 degrees Fahrenheit. So as long as we're here on Delmarva, where it seldom gets that cold, we can still use ice or salt on our roads to melt the ice. Now, if we were to move further north, like to Maine, where it might be -5 or 10 degrees Fahrenheit, -30 degrees Celsius, the salt won't melt the ice any longer. And so this is, again, the colligative property known as freezing point depression. You already know this if you've ever made ice cream. When you make ice cream, you have to surround the tub of ice cream with ice, and you have to put salt in there to get it to a lower temperature. That lower temperature is needed to freeze the ice cream. And so if we take a look at water, liquid water, H2O liquid, turning into solid, that's the temperature at which it freezes, 0 degrees Celsius. And so we get this sort of equilibrium established, you'll see that in the gizmos this week, that liquid water turns to solid water at the same rate that solid water turns to liquid water. And that is that freezing point. By adding the solute, the liquid water is decreased. And so the speed of freezing is occurring at a lower temperature. And that's when that equilibrium is established again. Here's another example of freezing point depression. So remember when water freezes, we've talked about water with those hydrogen bonds, that all the water molecules have to line up a certain way in order to freeze. Well, when we add a solute in there, take a look at the solute particles, salt, Na in blue and Cl in green. the solute particles sort of interfere with the hydrogen bonding of the water molecules. And this is what causes the water to freeze at a lower temperature, because the water particles are very attracted to the solute particles, more so than themselves. All right, so the next colligative property is called boiling point elevation. This is one that we've commonly seen. If at your house somebody's making pasta, you've probably seen them throw some salt in with the boiling water. That's not to make the pasta taste better. That is to increase the boiling point of the water. We call this boiling point elevation. And it's going to, like I said, it's going to raise the boiling point of the solvent. So a volatile solvent is one that turns into a vapor easily. Water is not volatile, but gas is volatile. Gasoline that we put in our cars is going to turn into a vapor very easily. Another example would be the antifreeze or coolant that you put in your radiator in your car. Antifreeze keeps the water from boiling just as well as it keeps it from freezing, so that your engine in your car can run correctly. So that's boiling point elevation. And what it does is it takes the temperature and increases it. And that's because of, as the water turns into a vapor, and that's one of the things you'll see in the gizmos this week, it creates a vapor pressure. You're not going to be responsible this week for vapor pressure, but you should be aware that it is a colligative property. So let me explain boiling point elevation for you a little bit better. So water boils when the vapor pressure equals the surrounding pressure. So see in this little pot here, you can see all of those pink up arrows because the water is evaporating. So as long as that's equal to the pressure of the air around us, then the water is going to boil. Now the problem is that when we add a solute to the water, again, sodium chloride, NaCl, you can see the sodium chloride is taking up some of the space on the surface of our pot, and it's not allowing us to have as many particles ready to turn into a vapor. Our vapor pressure, in other words, is not as high. And so what's going to happen is we're going to have to get this pot to a higher temperature in order for that water to boil. And here's just another picture of it up close so that you may be able to see it a little bit better. So here's our solvent, water, and you can see we've got evaporation of our solvent. Right there, we've got 3 solvent particles evaporating. Once we add the solute, salt for example, or sugar or whatever, you can see that our solute is taking up some space there, and so we're not getting as many particles evaporating. It's decreasing our vapor pressure, which causes it to boil at a higher temperature. Boiling point elevation. At the same time, it's decreasing our vapor pressure. So again, vapor pressure lowering is another colligative property. Here it is again, you can see it when we have pure water. We get a lot of water vapor particles above the liquid level. When we add the solute, we have fewer. And the last colligative property that you need to know is really great for us to be aware of, because this is one that affects our cells. And this is osmosis and diffusion, which I know you've studied before. So osmosis is the flow of water from a low solute concentration to a high solute concentration is really what it is. And osmosis is what we're going to be looking at. And this water then can flow through our cells, which are made of semi-permeable membranes. Diffusion is a little bit different, as you can see. And so here's just a little picture so you can see we've got a semi-permeable membrane right in between. Just like your cells would have. On the right side, we have all water. On the left side, we have water with a solute dissolved in it. And so you can see where the water is going. The water particles, the water molecules are moving towards the left. And so we have more osmotic pressure. Osmotic pressure, again, is one of those colligative properties. And so it only depends on the amount of solute, not the type of solute. And where would we see this? We would see this with our red blood cells. So here's some red blood cells. And the tonicity described here, hypertonic, isotonic, hypotonic, is telling us about how much water is in the surrounding cells. And so in the first one, it's hypertonic, and so water leaves the cell. A hyper, of course, means low, or excuse me, hyper so again, hypertonic, hyper means more concentrated, hyper, so we're having more solute in there. And so the water leaves the cells, and you can see that these cells shrink and they're not going to be able to function. Iso is a prefix that means the same. And so these isotonic cells, we're going to have they're going to have the same solute concentration inside as outside. So water is going to be able to move in and out of these cells. Hypo means, hypo, of course, is a prefix. It means less. So this is going to have less solute. And so water is going to come into these cells, into these red blood cells. And you can see those red blood cells swelling up. They can even burst open. So there are all of our colligative properties. I hope this helps you as you're going forward this week to study them.